Okay, so in this video, we are looking at related rates of change. So we need to remember something from our chain rule here. So why it's called related rates is I could find, right, the dy dx, right, the rate of change y with respect to x. I can find that by, say, using the rate of change of y with respect to z and the rate of change of z with respect to x. If I multiply them two together, we treat them like fractions, right? We treat them like fractions, they will cancel out, and I'll get dy dx. So this is what related rates of change is, right? We're essentially kind of using our little puzzle pieces we get within our questions to then form the answer we're looking for. So it's really important, right, to know if I have dy dx equals 8, it's important to note that if I want to find dx dy, that is just 1 over that. So just put it over 1, you flip it upside down, you find the reciprocal of it. For example, here dA dr is 4r, so therefore dr dA is 1 over 4r. If I was looking for dv dr, say for example dv dr, that was 2 over or, right? Dr dv will equal or over 2. So you just kind of flip it upside down. So related rates of change, right? So questions, they require to use a number of different mathematical concepts and ideas, right? Some are providing the question, and then some you have to kind of maybe use a formula, to find another rate that you're looking for. But anyway, how do we do a related rates of change question, right? So the steps are: draw a diagram if necessary. Step 2, you identify the rate of change looked for in the question. 3, you find and identify the rates given in the question. So you're given a rate in the question, you need to find and identify what that is and write it down. Then you need to set up the chain rule and then lining up the derivatives correctly and trying to find the missing link you need to find the derivative you're looking for at the end. And then you write down any other relevant formula with the correct variables. So think of like volume, area, surface area, perpendicular height, etc. And then you differentiate that to find the missing rate. Or you can use use these rates to complete the chain rule to find the required rate. So for example here, if I am looking for, say, dv dt, the rate at which the volume is changing with respect to time. So usually if they say in the question, find the rate, right? They say find the rate something is changing, and they don't specify another variable, they mean time, right? So dv dt, so all I know is I'm setting up my chain rule, I need a dv on top, and I need a dt on bottom, and my job is to sleuth through the question and find out what's my missing link here I can put in. So let's have a look at the question here. So a spherical balloon, that's probably important, is being inflated so that its volume is increasing at a constant rate of 24 centimeters cubed per second. Find the rate of increase of the radius when the radius is 30. So for this one, we don't strictly need a diagram here, right? But we might need a diagram, say, if we were looking at maybe like a cylinder or like a cone, right? Well, identify the required rate. So the rate I'm requiring to find is find the rate of increase of the radius. So the rate of increase of the radius, so how fast the radius is increasing. Well, that is just dr dt. We're looking to find dr dt when or is equal to 30. Now let's identify any rates I have made hidden in the question. Well, I'm reading back through the question here and I realize, okay, it's being inflated, the volume is increasing at a constant rate of 24 centimeters cubed per second. So that's telling me now I have the rate at which the volume is increasing. That's dv dt. So I have dv dt is equal to 24. This is the rate of change of the volume. Okay, Now I need to set up my chain rule. So I am looking for dr dt. So that means I need a dr on top. I need a dt on bottom. Well, now I need to find my missing link. Okay, what can I put here that I can easily find? And that missing link is actually going to be dv. Because I already have dv dt already, and dr dv. Well, how can I find dr dv? Well, I know that the volume of a sphere is 4/3 pi r cubed. If I differentiate that with respect to r, I get 4 pi r squared, and then I can flip it to find dr dv. So that would be 1 over 4 pi r squared. And there we go, I found the last missing piece of my puzzle. I have dr dv, and I have dv dt. Now, I just sub them into my chain rule. So dr dt, the rate of change in radius with respect to time, is equal to 1 over 4 pi r squared times 24. And then I know r is equal to 30. That's what we're trying to ask you to find. Find when r is equal to 30. The sub in r is 30. I get 1 over 150 pi per second. So that is how fast the radius is increasing. So it's increasing a very small amount per second. So let's look at another example here. So oil is dripping onto a surface at the rate of pi over 10 centimeters cubed per second, and it forms a circular film, which can be considered to have a uniform depth of 0.1 centimeters. Find the radius of the circular film is increasing when the radius is 5. So let's identify. So this oil forms a circular film on the surface, which can be visualized as a very flat cylinder. Like a very, very, very flat cylinder. Right, and the height is 0.01. Right, of radius or. So we need to identify the required rate of change. Well, the required rate of change, if I go through my question here, it's asked me find the rate at which the radius of the circular film is increasing. So I'm looking for dr dt when r is equal to 5. So let's now go scan through the question, find any rates are given. Well, oil is dripping onto a surface at a rate of pi over 10 centimeters cubed per second. So the volume of this like mini cylinder is changing at pi over 10 centimeters cubed per second. So the rate at which the oil is dripping is dv dt, which is pi over 10 centimeters cubed. This is the rate of change of the oil. So now we need to set up the chain rule. So remember, I'm looking for dr dt. So I'm looking for dr dt. I need a dr on top, dt on bottom, boom, boom, times it. What am I going to put in here? dv. So, write down any relevant formula. So I'm dealing with a cylinder. So I'm dealing with a cylinder, and the cylinder is given as pi r squared h, but I know h to be 0.1 in the question. Yes, right. And then differentiating v with respect to r. So if I differentiate v with respect to r, I have dv dr, which is equal to 0.2 pi r. So now to find dr dv, I flip it over. So if I 1 divided by this, I get 5 over pi r. Now I have dr dv, and I have dv dt from the top of the question here, which is equal to pi over 10, right? Sub them into my chain rule here now. So dr dt is equal to 5 over pi r times pi over 10. Then simplify it, I get 1 over 2r, then sub in r is equal to 5, I get 1 over 10. So the radius is increasing at a rate of 1 over 10 when the radius is 5. Right, so let's look at some example questions here. So 2024, the volume of a hemisphere is increasing at a constant rate of 450. Stunning. So I know dv dt is equal to 450. And what I'm looking for is find the rate at which the diameter x of the hemisphere is increasing. So find the rate at which the diameter x of the hemisphere is increasing. So I am looking for dx dt. So I need a dx on top and I need a dt on bottom. And well, looky here, I have a dv dt, so that's one of my missing pieces there. So that means I need a dv down here. So now I need to find something that I can get dx dv from. Give your answer in centimeters per second, correct to one decimal place. Remember, the volume of a hemisphere is given by this. We have the volume of a hemisphere. Stunning. So differentiate this. The volume is equal to pi over 12 or cubed. dv, x cubed, dv dx is equal to pi over 4x squared. That is dv dx. Sum it in. dx dt equals pi x squared over 4 times dv dt, which is 450. Note, that's a lie. That's a big fat lie. I'm a liar, pants on fire. Because I'm looking for dx dv, and I have dv dx. So I need to find dx dv, which would be equal to 4 over pi x squared. Now we can sub it in. 4 over pi x squared times dv dt, which is 450. And I'm looking to put that in for x is equal to 20. So dx dt is equal to 4 over pi times 20 squared times 450, which should give Moa an answer that is 4 over pi the answer should be the answer should be, oh sorry, correct to one decimal place. There we go. I'm using this new calculator. Hate it. Right. So my answer here should be 1.43 centimeters per second. That is my answer there. Right, let's look at another one. This is in 2021. A sugar cube is put into coffee. The sugar keeps its cube shape as it dissolves. As the sugar cube dissolves, its volume decreases at a constant rate of 1 over 20. Let x be the side length of the cube at time t. Find the rate of change of x when the volume of the cube reaches 1 over 64. So, what do I have and what am I looking for? So I'm finding the rate of change of x. So I am looking for dx dt. Setting up chain rule, dx dt, ding, ding, multiply. So what other information do I have? The sugar keeps its cube shape as it evolves. The sugar cube dissolves, its volume decreases at a constant rate of 1 over 20. So dv dt is equal to minus 1 over 20 because it's a negative rate. Other information I have is, well, I know the volume of a cube is the side length cubed. So v is equal to x cubed. So my missing link here is going to be dv. So I need to find dx dv. So dv dx is equal to 3x squared. Therefore, dx dv is equal to 1 over 3x squared. 1 over 3x squared times dv dt, which is minus 1 over 20. And then we're looking for when the volume of the cube reaches 1 over 64, but I have x's here. So volume is equal to 1 over 64, which is equal to x cubes. Cube root both sides, I get a quarter is equal to x. So now sub in x is a quarter, dx dt equals 1 over 3 times a quarter squared times minus 1 over 20. That will be equal to, if you put it in your calculator, minus 4 over 15 centimeters per second. Right, another one. So this one here, 2023. The diagram A below shows a square base pyramid whose base sides of length c units. The base of the diagram is horizontal and perpendicular. Height is h units. Diagram B shows the same pyramid. It also shows a horizontal square that lies within inside the pyramid, a distant x units down from the top of the pyramid. The area of the shaded square is given by this. X starts to increase at a rate of 3 units per second. This causes s of x to increase as well. Find the rate of change of s as x with respect to time at the instant where x is half the perpendicular height of the pyramid. Give your answer in square units per second in terms of c and h. So I actually have no numbers in this one. So what's asked me to find here? Find the rate of change with respect to time. Surface area s of x. So that is ds dt is equal to ds on top, dt on bottom. So what else am I dealing with here? Well, I know that x increases at a rate of 3 units per second. So that is dx dt. So my missing link here is dx. So I need to find ds dx. Now, but before I do that, what to say? The instant where x is half the perpendicular height of the pyramid. Well, h is the perpendicular height of the pyramid, so x is half of that. So h is going to equal to, so say a half h is equal to x, right? So x is equal to half of that height. So if I sub that in, s of x will be equal to right. So half of h is equal to x. So therefore, so ds dx, that's going to be to differentiate this with respect to x. So I'm just going to treat the c squared and h squared like a constant. Differentiate with the x, bring the 2 down, then multiply by the x. Then the answer here is just going to be 2xc squared over h squared. Then x is equal to half h. 2 times a half h c squared over h. So ds dx is going to be equal to c squared, h squared, sorry, over h, because one of these h's will cancel out here. That is ds dx. Then ds dt is equal to ds dx, which is c squared over h, multiplied by dx dt, 3. So my answer here is just going to be 3c squared over h. That is my ds dt. How fun. Right, what's in the home stretch now? Right, this one from 2016. Air is pumped into a spherical exercise ball at a rate of 250 centimeters squared per second. Find the rate in which the radius is increasing when the radius of the ball is 20. So, find the rate at which the radius is increasing. So I am looking for d or dt. I need a dr on top. I need a dt on bottom. Multiply. Any other information I'm given? So I am known air is pumped into a spherical exercise ball at a rate of 250 centimeters cubed per minute. So that is dv dt, the volume, the rate of change in volume is equal to 250. Therefore, my missing piece here is dv. The dr dv. So I know the volume of a sphere is 4 over 3 pi r cubed. dv dr is equal to 4 pi r squared. Therefore, dr dv is equal to 1 over 4 pi r squared. So sub it in, dr dt is equal to 1 over 4 pi r squared times dv dt, which is 250. Then I'm looking for it when the radius is 20. So dr dt is equal to 1 over 4 pi 20 squared times 250, which will equal to, calculate are correct, so this will actually be 2 pi over 32 pi. 5 over 32 pi. So there it is. Find the rate at which the surface area of the ball is increasing. So now I'm looking for the surface area with respect to time. I need a dA on top, dt on bottom, boom, boom. My missing link is going to be dr because I have dr dt from part 1. So I need to find dA dr. Well, the surface area of a sphere is equal to 4 pi r squared. So dA dr is equal to 8 pi r. Then r is equal to 20. That's what it says here when the radius of the ball is 20 centimeters. So dA dt is equal to dA ds, which is 8 pi times 20 times dr dt, which is 5 over 32 pi. And then my final answer here will be 25 centimeters squared per second. That is dA dt. Last one here. A spherical ball, a spherical snowball is melting at a rate proportional to its surface area. That is the rate at which the volume is decreasing at any instant is proportional to the surface area at that instant. Prove that the radius of the snowball is decreasing at that constant. So dr dt. I need a dr on top, dt on bottom, boom, boom, multiply. I can already tell before reading this, my missing link is going to be dv, the volume. So, the snowball is melting at a rate proportional to its surface area. That means it kind of goes up in a multiple of its surface area. So, that means dv dt is equal to some value k, right, times 4 pi r squared. Let's say minus k because it's decreasing. Then dr dv, well, v is equal to, again, 4 over 3 pi r cubed. dv dr is equal to 4 pi r squared. Therefore, dr dv is equal to 1 over 4 pi r squared. dr dt is equal to 1 over 4 pi r squared times dv dt, which is just minus k times 4 pi r squared. And so look, we want to prove that the rate that's always decreasing at a constant rate. So this 4 pi r squared will cancel with this 4 pi r squared. Then I'm left with dr dt is equal to minus k, i.e. a constant, i.e. at the same rate. Hey, that's this video done. Hopefully related rates are a bit better for you now. Hope to do some help, and I'll catch you guys later. Bye.